And we have to now saw off or cut off in some manner with a torch or some manner, or if they're small enough gates to feed the workpiece, then you can break them off if it's a brittle material, say like cast iron. But this is the workpiece, and we have to detach it from all of this which was necessary to make the casting. And in the next slide you just see the final piece that we have sawed off, and that's the gate. That's the little gate that we had feeding the material, and we'd have to dress that off to make it fit. Using this technique now, you can make precision castings. Well, you know this if we can use this technique to, say, make a bridge that would fit the inside of your mouth, all of the contours and everything that you have in your mouth. So what I'd like to do now is to just follow through that sort of technique to show you the steps that you have a lot of fun with, because you can do this in your kitchen. As I said once before, you don't really need an extravagant laboratory. If my wife is here tomorrow, you ask her, she'll tell you that I'm forever messing up her frying pans because I get the grease out of them by melting tin in them. But nevertheless, what you can do is this. Let's suppose you wanted to be a counterfeiter, and you know you can't just counterfeit coins, you can counterfeit, say, statuary. And suppose I had a real small statue that I wanted to copy, a little head of Beethoven or something, and I wanted to copy it. Well, the first thing I have to do is to make a mold to produce the wax. And you notice I left that step out in the slides, right? I didn't tell you how you made the wax, but you're going to have a mold to make the wax. Well, in antiquity, they did it this way, and in fact, we still do it this way if we don't have any pieces to produce. We'd take that, say, head of Beethoven, or that little thing, and we'd study it to find out where we could put a parting line so that we'd have no reentrant angles in a piece mold. And generally that would be found by coming up your neckline and following your ears around like that and up to the top of your head. So if I made a casting of the front of my face, say a life mask, I could strip it off and I wouldn't pull my nose off or anything like that. There are no reentrant angles that would bother me. And so you make a split mold, a plaster of Paris. And plaster of Paris is gypsum, a calcium sulfate, and it has water of hydration in it. But we get this particular material and we just cast the one half of the head in it, and then wax the surface and cast the next half, and then the plaster Paris mold will come apart on that waxed line. When you get it apart, then you can put it back together and get it wet, soak it, get it wet. And if you get it wet, since water and wax don't mix, you can pour wax into the plaster Paris mold, and it won't run into the plaster Paris. The molten wax won't. So it solidifies, and you can separate it, and you take out your wax. So that's your model. Now that means you can make model after model after model after model. Is this precise? Do you know this is so precise that if I did that for your thumb and made a split mold, I could copy your fingerprints, and then I could make, instead of making a metallic material by this method, I just make a rubber material by that, and I could put it on my thumb and rob banks and leave you a fingerprint, right? But I'm trying to tell you how neat, how precise now you can pick up the image, and you can pick it up delightfully. And so this is what we do, and we have the wax. We go through the steps I've just described to put it all together, and now we need to invest it. And what are we going to invest it with? It turns out plaster Paris is a perfectly good material to invest it with. So I take the wax and I just pour plaster Paris all around it, and now it's solidified. The plaster Paris sets up. But now I have to do two things. I have to take the wax out, and I do this by heating the mold up, and the wax runs out. And I also have to take the water of hydration out the plaster Paris, so I have to heat it to a high temperature, like 1200 degrees Fahrenheit, then let it cool down and pour molten metal in it. I could pour copper in it. I can pour very high temperature metal in it, and I can get the image back out. So that's Sir Perdue, and that's a method that we use for making very intricate things like turbine blades.
In sand casting, a flask holds the sand mold. Molten metal is poured into a basin, then flows into the mold cavity. Often a mold core is used to produce hollow parts. The lost wax method of casting is used to make such items as jewelry, statues, dental bridge work, and turbine blades. This method is also known as investment casting. In this process, a wax pattern is added to a flask, and a mold slurry, like plaster of Paris, is poured around the wax. After the slurry hardens, the mold is heated and the wax runs out, leaving a mold cavity into which molten metal is poured.
Well, it isn't the only way we do hot working. This investment casting isn't. We also do things like hot rolling, and in hot rolling, we just have to have a rolling mill, just any old kind of rolling mill. Now, the rolling mill can be a matched set rolling mill. It could have grooves in it so that instead of rolling, say, sheet stock with two flat rolls, as would be indicated here, we're going to roll materials like, say, railroad rails or I-beams or H-beams or long complex shapes. And all we have to do is to have mold shape that will allow us to roll that contour. Generally, now in a case like this, let's suppose that we have a slab this thick, and we want to get out of that a slab that's a sheet that's about as thick as that arrow. Well, you say, well, why don't you just take the rolls and screw them together so that we just have a gap in the middle that's that thick? Well, the fact of the matter is it would require too much work. Despite the fact that the metals are going to be hot, it still takes a lot of energy to plastically deform them, and so there's going to be a limit of whatever the roll will accept and the power that you have to push it through the roll. So what we do is we have a roll after roll after roll after roll. We can have these as tandem rolls, or we can have these two rolls that we have shown here so that you can screw them down, pass the material back over the top and run it through again if the roll is running in one direction. Or you could have a 3-high mill with a roll in the center, and you run the slab through the top onto a bed on the other side, then run it back through the bottom. And all you have to do now is continually elevate and deviate the middle roll, and that's a 3-high mill. Or you could have a roll set and not change its setting, and right behind it a second roll that's set for a lower gauge, and then another one that's for a lower gauge. This is called tandem mills. And when you do that, you have to appreciate now, as you're reducing the material in thickness, it's getting longer. And so the second mill is going to have to go faster than the first mill. And so if you go into a steel mill and you watch them roll, say, hot strip, you'll see them put a slab in the beginning, and when you look at it, it looks like it's crawling through the rolling mill. And it comes off of the last mill going about 1,800 feet per minute. And you have to catch it and coil it. But nevertheless, that's how fast it goes. So we can hot roll material and produce a product. Actually, if we don't want to roll it, we can do a lot of other things. We can take the material and stamp it or forge it. And this is just an indication of a forging die. Now, actually, if you're going to forge something like this, you have to have a piece of stock that's going to be approximately this size. And you generally have several steps in this. We'd have dies that would blank out a piece, let's say a bar or a rod, into this approximate shape, then clip off the excess material from that shape, and then put it in this particular die if it's a finished part, and then put a pressure on top of it and forge the piece. And it's sort of a piecework. It's not a continuous operation as you would have in a rolling mill. So we have a lot of these particular piece type operations to hot work a material and get it into shape. And one of these is an extrusion, and this is the basic setup for an extrusion press. We have to have a very high pressure to extrude a metal. Everybody knows a lot about extrusions. Everybody that uses a toothpaste tube does, because every time you squeeze the toothpaste tube, you're making an extrusion of toothpaste. And when you do this, you know that it requires pressure to squirt it out of the hole. You also know that if that hole gets closed up, gets smaller and smaller, it takes more and more pressure to squirt it out, right? And I don't know whether you've ever done this, but as I certainly see it done by my grandchildren, if you leave the cap screwed on the top and you squeeze it hard enough trying to get it out when there's no hole, then you break through the side wall, right? And so on this slide, what we see then is that we have to have this cylinder, which is on the top of sufficient strength now, so that when we put the pressure on by pushing the ram against the material, which is going to be in the center, that it will squeeze it through or squirt it through that little hole that goes through here. Now, actually, in a hot die, we have a situation that looks like this. We have a ram, the plunger that's going to come in now to push the material out of this end, We have a die that's independent of this heavy section that we have, this container that we're going to put the metal in. And that means that we can use the container for lots of different die designs. We could say in the aluminum industry you'll find them extruding, hot extruding, all sorts of shapes, like channel beams, I-beams, and triple track, anything you want out of a die that's all in the same flask, all in the same press container here. But if you put the material in the die and you have a ram, you want to have what's called a dummy block, and this does two things. Now, it fits more tightly than the ram does, and therefore the friction that you have as you run the ram down is about the same all the time, whereas if you just ran the ram down and had to have that tight a fit, it would increase the friction. And it also allows you to work with a hot piece without heating up the press ram too much. And so we extrude it through the die, and we get this long rod that, or bar, or whatever we want, that comes out the opposite side. So we not only have to do, not only do hot rolling, we do hot forging, and we do extrusions, and we can also hot work by doing wire drawing. Now in the next slide we see actually a wire drawing die, and this is typical of a hot drawing die or a cold drawing die. It doesn't make a whole lot of difference. If you ask yourself some questions, you will find out that you have a little problem here, because I have something that's big and I want to push it through that little hole. Excuse me, I want to pull it through that hole. I want to pull on it. I'm not going to push on it now. And the material has a certain yield strength, right? If the cross-sectional area is less and I'm pulling on it, the stress on this side is going to be higher than the stress on that side. True? So it looks like that we would pull this material in two before we'd ever pull that material through the die. But the fact of the matter is, we can do that if the draft or the reduction in going through that die is too great. So we have to, for the material that we're looking at the temperature we're going to work it at, within the period of time that the material will relieve the strain that you put in it, and there is such a period of time, that is to say, when I pull it hot, I'm going to cause it to become harder for just a very brief period of time, and then it's going to recrystallize, it's going to reform, it's going to relieve the stresses, it's going to reconstitute its stress. So there's a time factor that goes in this, but there's a draft factor that allows us to pull the material through hot.